What else do we have? Here you. What am I doing? There we go. All right. So those answers are there. You don't have to do the calculus to integrate that rate law. If you are interested in that type of thing, I put that here. You're more than welcome to go through there. In reality, out of the past 5 tests, 2 have actually had you use that, in one of the free responses, but not integrating it, just using like this version. And first order is the one that is used way more often. But as I showed you yesterday, a lot of times they like to put graphs and stuff like that on there. And I think tomorrow we'll go over some of their type of crazy questions that, seem like a little bit more difficult because of silly tricks. If you are very interested, I put the end all be all of, this is chemistry for chem majors in college. You can go through this all you want, but it is overkill for sure. So you're more than welcome to do that. All right. Today, and we want to discuss elementary reactions, perform some AP questions dealing with that. Tomorrow, review rate laws, catalysts, and diagrams. Yeah, so that tomorrow, basically, I'll just go through a few questions for you. The reason for this is Monday's asynchronous thing is basically going to be the progress for Unit 5 kinetics. I am going to open that Thursday, and basically I'm going to go through some questions. Friday, we'll do a very light start on thermodynamics. Basically the stuff that you went through in X chemistry or even CP. If you were in CP, it'll be the very beginning of that. So don't think that I'm trying to load you up for this asynchronous thing. I saw an email from a student and they were like, please don't kill us with work on asynchronous day or whatever. I'm cool with that. So I'll open it up here. Take it easy on you these 2 days, and then we'll see what lies on the asynchronous day in the future. If you don't have any clue of what that means, is Mondays are basically all Canvas and teachers are in meetings for the whole day. So that's what that is. All right. Without further ado, let's look at the question that you guys did last night, the 1981 B. Take a look at that. And then we'll go over elementary reactions. My visualizer is not working. There we go. All right, so if we take a look here, and I will go ahead and put all of these free response questions. I'll go ahead and put the answers to all of these up there, probably by Friday. But basically, it's just very similar to the one we did together earlier in the week. They give you 6 experiments. You're given the initial rate of the reaction and the initial concentration of the reactants. So again, what you want to do is you want to look for, if you can, you want to look for times where the concentration is maintained for one of them, and it changes for a different one. So it looks like for rate 4 and rate 2, or experiment 4 and experiment 2, we have 1.120 for B. So it looks like we're calculating for A. So again, we take the concentration to the X power over the 0.24, which is the concentration for rate of 2. And then you divide the trial 4 by trial 2. You do the same for the rates of reaction, and then you get 0.5 to the x equals 0.25. X equals 2. Now, if you have difficulty doing this math in your head, remember, if you take the log of the rate of change, let's just put change in rate, over the log of change in concentration, then that will get you that 2. So if you take the log of 0.25 divided by the log of 0.5, that will get you the 2. The other trial we can use for this is here, 5 and 2. So we get 0.06 and 0.12, and then 1 and 2. One of the things that you may not know is if you're having to do this without the calculator, like it's the multiple choice portion, it doesn't matter if you take this divided by this or this divided by this, as long as you do the same with this. And you can see if we take 0.12 divided by 0.06 and 2 divided by 1, we're going to get 2 for both of those. So we're going to get y equals 1. Or if you do it my way instead, the harder way, but you have the calculator, you get 0.5 equals 0.5. So that's first order for y. So then remember, when we write our rate law, we need the K, and we also have the concentrations of the reactants to their order, or to that powder. And it says C, calculate the value for K. So does it give you a specific trial? Nope. Which one did I use? Looks like I used trial 1. So we have the rate equaling 8. And the key thing here is if we take a look, they're going to have you specify this units all the time on this case. So it's molarity per hour on top, and then molarity squared and molarity on bottom. So if we take a look here, you get molarity cubed on bottom. You got that molarity on top still, so you cancel out one of those. Since this is on bottom, it's going to end up being to the -2nd. Ours is on bottom to the -1st, or you could have put like 289 per molarity squared hour. But that's more commonly the way you're going to see it. D, calculate the value of the initial rate of this reaction at 30 degrees Celsius for initial concentration shown in experiment 6. Basically, they want you to find this. So since you found the K, you're going to plug that in. And what you're going to notice is that that rate, since this is molarity squared, and you have second order here for your concentration of A, or for your order of A, that molarity squared is going to cancel out. You're going to still have that per hour on bottom, but the first order for B is going to give you the rate unit molarity per hour. Basically, just multiply all that through. E, assume the reaction goes to completion under the specific conditions in experiment 2. So what you need to do here is you have this concentration and this concentration. You need to figure out from 0.240 of A, how much C you can make, and from 0.120 of B, how much C you can make. You might be able to sit there and see in your head immediately that B is going to be the limiting reagent because it takes 2 for every 3 versus 1 for every 3, and you have less B. So that might be something that you can do quickly in your head. So out of these two, which one is the correct one? It's going to be the one that makes the least, because this was the limiting reagent for that. All right. As I said, for this, the Arrhenius equation, it specifically said on there that it's not required. Just to give you an idea of what this equation is showing you, is that K is dependent on the temperature as well as the activation energy. So if you add a catalyst, it's going to lower this energy of activation. And since this is negative, that's going to make K higher. Since the temperature is on the bottom, the higher the temperature, the higher the K. Keep in mind that's because of this negative sign. A of E is basically how well your reactants are at colliding and being successful. They call it the frequency factor. Steric basically means like if something is going to get in the way of the collisions. So steric factor is another term for that. If something changes or whatever, we'll go back to that. Basically, all that formula does is allow you to see that K is both dependent on temperature. And we said rule of thumb, for every 10 degrees, K doubles. And K is also dependent on if there's a catalyst present, the activation energy. Because the catalyst lowers that activation energy. All right, reaction mechanisms. So a lot of times we look at a reaction and we basically look and see reactants form products. In reality, sometimes there's multiple steps for this. So if we have, 1 second. Sure. Yep. Fine. If we have these pathways that we talk about, sometimes there's multiple pathways, and there's something we call intermediates. These intermediates form, and maybe they break apart and form the products, or the intermediates form other intermediates, and then finally you get to the products. Well, if you have the rate law, and if you have the ability, you can actually kind of break down an entire chemical reaction into what we call the elementary steps. Now we know that if you have a balanced equation, like full-on equation, that the rate law is not dependent on the coefficients for that. But if we are able to look at these elementary steps, you can build rate laws off of each step based on the coefficient. So keep in mind, this is only if you're dealing with elementary steps, can the rate law be determined from the coefficients of the reactants. So they have something called molecularity. There's unimolecular, which means you have first order. There's bimolecular, which means you have a combination, either 2 different reactants or a coefficient of 2 for the same reactant, and that would be second order rate law. And ter, it means 3 basically. So termolecular refers to a combination of 3, which means it's third order overall. So we know that the more molecules, the more collisions, the faster the rate. The faster the molecules are more moving, so higher the temperature, the more likely they will collide with enough energy, and the higher the rate. Keep in mind again, the molecularity of an elementary reaction is its order. This is not true, since we're talking about elementary reactions here. This is not true for a overall reaction. So we know that so far that rate laws are determined through experimental data. Well, a reaction mechanism is also determined by experiment. We have something called the rate determining step, and that is what's marked as the slowest step. Imagine it like this: when you went to get your license, like you had to sit there in line first to get up to the counter. You then had to take the test. Then you had to go take the eye test. Then you had to get your picture taken. Then you had to wait for it to process. And everybody, most people do not enjoy the DMV because it just seems so long to get through all these processes. No matter how many people you have taking a picture, they probably would not make that process any faster. No matter how many eye machines you have, it's still, that may be the factor, but it's probably still not going to change the overall process. So there's something in there that's making everything, slower. And that's what the rate determining step is. Just like the airport, you know, there's so many lines, but all of it comes to the end. As after you get through all that garbage, you still got to sit there through that single file line going into the airplane while, you know, Tommy Panic is sitting there trying to shove his baggage into the overhead compartment. So, I mean, there's always these slowest steps. So, reaction intermediates are a thing. So basically, we're going to take a look at those in a second. They're produced, but then they're consumed. They cannot be in the rate law. So if we take a look, you're given this reaction mechanism. We have two-step mechanism. One is the slow step, one is the fast step. We want to look for intermediates. So if you recall, this is similar to the cancellation process you did in Hess's law in earlier chemistry classes. So if we take a look, we find something that's on both the products and reactant sides that we can cancel out. So this NO2 here, or N2O, this is an intermediate. So we're not going to be concerned with that for the overall reaction. I believe that that's our only intermediate, right? So if we take a look, if we were to add both of these together to get the overall reaction, we have 2H2 plus 2NO yields N2 plus 2H2O. So that's the overall reaction that you would normally see without looking at the mechanism broken down. We don't see the intermediates in here. To find the rate law, we take the rate determining step and we base it off of that, determining. There we go. So the rate equals K. We have H2 and NO. Now again, since this is an elementary reaction and this is the slow step, we can use this coefficient to figure out the order for this. It's second order in NO and first order in H2. You can only do this if you have the broken down mechanism and you know the determining step.
So will it always be labeled slow step, fast step on anything we do, like the two equations?
Yeah, or it may say rate determining step.
Okay.
Yep, you got it. A lot of times, and this is actually the process of the mechanism too. So this is actually the first step. This occurs where H2 reacts with NO, right? And then it makes this N2O. That N2O then reacts with H2O, right? I'm sorry, these are the products. That N2O then reacts with H2 to make N2 and H2O. So this reaction occurs to make these, then this reacts with your initial of this to make these two things. Same thing with this. Now, keep in mind, we don't see the intermediate in the overall reaction, and our rate law must be determined from that slowest step. Sometimes your slow step is the second step. So this occurs first, and then this occurs. But it's just like we said before. Let's say you sit there and you make it through security at Indianapolis Airport real quick. You still may be waiting, in line depending on which zone or whatever you're in, right? So you do need to keep track of this. So let's take a look here. H2 plus ICl yields HI plus HCl. The HI then is the intermediate, so that's going to be used up. I think that's it. So the overall for this is H2 plus 2 ICl yields I2 plus 2 HCl. Since this is our determining step, we base our rate law off of that. H2 and ICl. So there we have, since we're only using this slow step to form this, the coefficient for this is 1, so this is first order in hydrogen, and the coefficient for ICl is 1, so this is first order for ICl. Now, very rarely do they sit there and use these terms, but I mean, that's why they're there. So that would be considered a bimolecular elementary reaction. 1 and 1. This one would be considered termolecular. Now you're sitting there saying, oh, wow, this is easy. It does have a little bit of trickery to it. If your slow step is the second one, that means that that's the rate determining step. That means that an intermediate could be part of your thing. That's a problem. Let's see how we fix that. We do the same thing. We cancel out the intermediates. We get 2NO plus O2 yields 2NO2. Now, the problem with this is that our rate is going to be equal to K, concentration of N2O2 and O2. This is no good because, as you know, every rate law we've done before this, we have only used the reactants of the overall rate law. So since this is an intermediate, this cannot be a rate law for this reaction. Anybody have an idea of how we can figure out how this part of the slow step will be determined? No, okay, it's okay. So if we take a look, we know that N2O2 is part of the slow step. Well, in order for the concentration of N2O2 to go up, we need to deal with the concentrations of the 2NO. This is a fast step, so we're going to put that, we're going to switch this out with this. So the rate is equal to K, and then that N2O2 will be the concentration of NO. Since this is a 1 to 2, and it's a 1 here, 1 to 2, that becomes 2, so that is second order. And then the O2 again is still first order. Now, even though that matches up with this cannot allow you to determine this. It must be done from this reaction mechanism or from experimental data. As we saw here, H2 plus 2ICl, this is not second order because of the coefficient in the slow step. All right, so now we have a big, huge jump. We have, first of all, bromine breaking down. We probably have light or something like this here to break that down. Then we have Br plus H2, yielding HBr plus H. That's the slow step. We then have Br2, also reacting with the H that was formed here to make HBr and Br. And then we have 2Br forming back into a Br2. So let's determine what the overall reaction is. So I have a Br2 here, and I have a Br2 here. I have an H here, and I have an H here. I have a Br here, and I have a Br here. I have a 2Br here, and I have a 2Br here. So there are all my intermediates. So if we take a look, the overall reaction is just Br2 plus H2, right? You might be feeling like you've lived a lie with chemical reactions now. Like this simple reaction is actually undergoing all of this process. And notice the HBRs here are both on the same product side. So that is 2HBr. Now for the fun part, we need to look at the slow step. K times the concentration of Br and H2. Each of these are in first order. Well, we cannot have Br because it is an intermediate. So we need to find something that gives us Br2 from Br. That would be the first step. The problem with that is we have a 2-to-1 ratio. So that means for every 2 of these, we get 1 of these. Well, what does that mean? Well, we take Br2 to 2Br and we divide it by 2 to get 1 to a half. So that means for this Br2 for this reaction, this is going to become K to the Br2. But what is the coefficient after we rebalance this out? 1/2. So that is to the half order. And then H2 is to the first one.
And how do we get that 1/2 again?
So we notice that Br here is in the slow step, but we cannot use it because it has to be from our overall reaction. So we go up here and we realize that how can we make this Br instead of 2Br? We need to divide this entire equation by 2. That gives us 1/2 Br2.
Thank you.
You're welcome. Last thing on this, and unfortunately, this was a late addition on my part. So you might, I'll tell you what, maybe I'll just add this whenever I take the pictures for the other things. But there was one question on one of the AP tests like from 5 years ago. So I just want to make sure that you see this. If we take a look, if this is our overall reaction, we have step 1 and step 2. This is a slow. Apologize for my handwriting. I did this pretty quickly this morning. I want you to go ahead. Actually, I think maybe you should at least write down somewhere the intermediates. Share those states of matter down there. All right, if we take a look, these H2O liquids are on the same side. This H2O aqueous, since everything here is in aqueous, that's going to be fine. We're not going to worry about that one. The H2O liquids are on the same side, so that's how we get the 2 H2O liquid. The O2, that's how we get the O2. So the only intermediate here is actually this IO negative. Now you might be looking at this and saying, oh, but what about this guy? Well, take a look here. This is used up in this first reaction, and then it's reproduced in this second reaction. What type of compound do we call something that gets used and then would reform? Well, here's a little hint. It's written above the arrow.
Catalyst.
You got it. That is actually a catalyst. Now, here is the deal. If the catalyst is in the rate determining step, that means that it actually ends up in our rate law. Give me 1 second, make sure again. Okay, yep, here we go. There we go. Sorry about that. That's what I was missing. I was sitting here looking at this like there's something wrong. Is it because this is aqueous? No, it's because we have H2O2 aqueous reacting with this catalyst and then breaking down into water And that catalyst then is the intermediate, but it reforms here. If that catalyst is in the slow step, it has to be put into the rate law. That is a little bit, I think, anti-intuitive maybe, because we've already said that we know that it's going to contain this, H2O2. Keep in mind, we don't go by the overall rate, we go by the rate determining. So we have the H2O2 here, it is first order. And then we are going to have that catalyst. There's no way that we could get rid of this because it is in the rate determining step. It has to be there, even though it's not clearly a reactant in the overall reaction, it is present here. And we do know that the rate can be dependent on the concentration of the catalyst, right? If we take, for example, we'll just take a look at a catalytic converter. Like I think in your chemistry class before, you probably watched that breakdown thing where they break down the catalytic converter, and it's got like over a football field of surface area in there, right? So if we take a look, that's going to be I negative. And it also is to the 1, so that would be our rate law. So for this, the catalyst must be in the rate law. If it's in the rate determined, if it is in, that seems like the most 2-letter words I've ever put in a while. If it is in the rate determining step. Step. Oh. Oh, all right. Last but not least, we've talked a lot about catalysts. Oh, actually, I want to do one more thing with this. Don't have any information on the endothermic and exothermic of this, so I'm just going to do it very generically. What do they call it? Reaction coordinate or reaction progress. If we were to look at that same old thing, with the catalyst and all that, and the fact that we have 2 steps, right? Or let's not even throw the catalyst in there yet. Let's go with something where we have 2 steps, like this right here. So I'm going to put generic there. Since we have 2 reactions going on, that means that if we look at this potential energy versus the reaction coordinate, we're actually going to have 2 humps. So this would be step 1, and this would be step 2. You can see they have to get the activation energy here, and then they form these intermediates, which are short-lived to get the products. Again, this overall reaction is exothermic, but that first step there, it looks like it was endothermic. So step 1 was endothermic, overall reaction, exothermic. Very generic one, but no matter however many steps you have, if you had to draw the potential energy versus the reaction coordinate, you would have as many humps. And if this were instead endothermic, then obviously this would be up here. Oh, I'm a little bit behind. Up here. Up here, up here, up here. We basically, I think, ran through a lot about the catalyst. We said that it lowers the activation energy or activation energy barrier. How does it do it? It alters the mechanism or has a different pathway. If you did not have any clue that these mechanisms existed before, now that may make more sense to you. They're not altered during the reaction. As we saw, catalyst was used up. The intermediate state goes away and the catalyst is reformed. Lowering the activation energy, speeding up the reaction. Yeah, It's amylase in your saliva, or peroxidase in your cells that breaks down peroxide, or helicase. These are all enzymes. The biological catalysts basically have a certain protein folding and specific shapes, so they react with specific molecules. And here's one that comes up a little bit. If we talk about heterogeneous, the catalyst is in a different phase than the reactants. So if we imagine the combustion of gasoline, the catalytic converter is basically this box with all of these little tubules in it and this metal, platinum and I believe rhodium, that these act as the catalyst. That would be a catalytic converter. The state of matter for the catalytic converter, these elements, is solid. The products of the combustion of gasoline are gas, they're vapors, right? So that would mean that the catalytic converter is a heterogeneous catalyst, meaning that since this is solid and the reactants going through it are gases, they are in different phases. A homogeneous, the catalyst is in the same phase as the reactants. So if we take a look here, aqueous, aqueous, homogeneous catalysts. Now that this reaction here, this is an iodide. That's one way to catalyze the decomposition of hydrogen peroxide. You can also use light. As it says, this is why we store peroxide in a brown bottle. Also why a lot of like orange juice and stuff like that, those are stored in darker bottles. If there's a dark bottle, usually there's a reason for it, because it's more costly to put something in a dark bottle. Usually that's because some type of chemical reaction could take place with light, breaking down something that you don't want broken down. You could also use manganese dioxide or manganese 4 oxide. And that would be, since this is aqueous and this is solid, that would be a hetero. So this one was homo, this one is hetero. This one is just with light, so that's not really a phase of matter, that's just questions. That's a lot to dump. I did record this, so if you need to go back through this, by all means, I'll probably put up some other videos and stuff like that, help you out on that. So let's do this one for homework. So you're going to have to do basically the stuff that we did before. And then once you actually have the rate determined from the experiment, you're going to need to look at these two methods, these two mechanisms, and determine which one is actually plausible. That one, did that one, and this one is very similar. So 1984B and 1991B, please try those out for homework. Again, you need to give the rate law of each of these based off the experimental data. Oh, look at this. Then they actually give you concentrations and ask you how long must the reaction proceed to produce the concentration Z equal to that. And then at the end, you need to select which of these reaction mechanisms will work. Oh, I just realized. I don't think we've done one like this yet. What's different about this one than any one that we've done so far? Anybody see it right off the bat? I'm terrible at the chat. Possible to write that down, yeah. The chat I never look at, so yeah, you're gonna have to rewatch the video probably. It's always better to, the chat's never on my screen. Sorry about that. Anybody see what the problem with this is?
Looks to me like fluorine doesn't have one where it stays the same.
Excellent, good. So you know that you can find fluorine like this, right? By using this one right here, you can find the order of fluorine.
Yeah.
Yep. So if we take a look at that, we can find the order of fluorine. We can find the order of ClO2. All we got to do is take the same thing that we did before. Let's use experiment 3 and 2. So you take the rate of 3 over the rate of 2, and that equals 9.6 times 10 to the negative third over 9.6 times 10 to the negative third. We're going to set that equal to, and here's the trick. Since we know the order of F at that point, you will know the order of F. We're going to know how to basically multiply this through. So we'll have 0.20 to whatever F's order is, divided by 0.40 to whatever F's order is. And then the ClO2 will be the hard one. We'll have the 0.20 for that and the 0.10 for that, but we won't know this. After you use this information to find the order of F, you can place it down into here, and using the concentrations of the initial order for F, place it on there. Now, the other thing that would be here would be the K. Well, what's going to happen to the K's immediately? They will cancel. So basically, we've always just taken one or the other because we made one cancel. Since we cannot make one cancel this time, basically we take the rate to the rate divided by the rate, and then we take these to each of their respective orders and compare them with each other. And normally, for example, if we were doing this with F, the 0.10 and the 0.010 and the 0.1010 would cancel out. So that's one thing that I think that we probably have never done. So that may be a little bit trickier for that. Don't think that we have that issue on the last one. Oh, look at that. Looks like we do. So both of those are definitely the harder ones of the group. Don't forget, my support hours today are from 10:30 to 11 o'clock. If you do need me to go through something, by all means, drop back in. I didn't expect to talk that long. Sorry about that. If you have any questions, by all means, drop back in by then. Sorry I didn't see the chat until later. Never look at the chats. Have a great day, guys.
Thank you.
Thank you.